In this video tutorial, I'll go through the practice questions proposed for the grade 12 ASP end of term 2 exam. I'll solve the questions and explain the answer key. So the first topic included in your exam is topic 2.2 and 2.3, which is about the solubility products and how to calculate the KSP and how to calculate the solubility. So let's first begin with the first question. The concentration of fluoride ions in a saturated solution of barium fluoride is. So they want us to find the concentration of fluoride ion. All what we have in this question is the KSP product. So first of all, I'm going to begin writing the equilibrium equation of barium fluoride when it dissolves in water. And you should always follow these steps while you are solving. So as you can see, this is on a ratio of 1 to 2. So I get 1 barium ion for 2 fluoride ions. So therefore, the solubility is S for barium, and for fluoride it is 2S. So when we calculate or when we write the KSP expression, it's the concentration of barium multiplied by the concentration of fluoride squared. Now here they want us to find the concentration of F minus, but I don't have yet the concentration of barium, so I need to use the solubility. What I'm gonna do, I'm going to substitute the solubility for barium and the solubility for fluoride, because concentration of fluoride is equal to 2S. So once I calculate S, I can multiply it by 2 and I can get the concentration of fluoride. So let's find S first. So the KSP is given to us 1.7 times 10 to the power negative 6. So 1.7 times 10 to the power negative 6 is equal to 4S cube. Therefore, S is equal cubic root of 1.7 times 10 to the power negative 6 over 4, and that is equal to 7.5 times 10 to the power negative 3. That is the solubility. Now I found S. All I need to do now is calculate the concentration. They didn't tell me find the solubility. They told me find the concentration of F minus. So it's going to be 2 times 7.5 times 10 to the power negative 3. And the concentration is 1.5 times 10 to the power negative 2 molar. Now if they ask to calculate the concentration of barium, it is equal to S. It is equal to 7.5 times 10 to the power negative 3. The solubility of manganese 2 hydroxide MnO2 is 2.2 times 10 to the power negative 5. So the solubility is, so in this question we are dealing with MnOH2. Always begin by writing the equilibrium equation. So again, this is a ratio of 1 to 2. So it is S, and here it is 2S. But in the question, they gave me S. The solubility is 2.2 times 10 to the power negative 5. It means this solubility is 2.2 times 10 to the power negative 5. What is the KSP? KSP in here, it is equal to Mn2 plus multiplied by OH minus squared. Mn is equivalent to S and OH minus is equivalent to 2S squared. Remember, the number that should be here should be the same as this one, because If, for example, I have 3 here, I'll be writing 3 here. So it would be raised to the power of 3, and here it would be 3s. I hope you understand what do I mean by this. So KSP is equal to 2 squared is 4 and s squared, and s is s cubed. So that's the expression of KSP. Now having s, KSP is going to be 4 multiplied by s, which is 2.2 times 10 to the power negative 5 cube. Don't forget the cube. The answer is 4.3 times 10 to the power negative 14. KSP comes without a unit, but solubility S has a unit of molar and concentration has a unit of molar. Now sometimes, like in the question over here, they might ask you to find solubility, and they want the solubility not in molar, not in mole per liter, they want it in gram per liter. Let's do this next question. The KSP of calcium fluoride is 3.9 times 10 to the power negative 11. So they gave me the KSP to be 3.9 times 10 to the power negative 11. Now this one over here is 1 to 2 ratio. So I expect it to be S with 2S. I'm going to show it to you on the equation. When I write CaF2 solid, it ionizes into Ca2 plus and 2F minus, AQ. So here I can write S, and here I can write 2S. I can also put the full ICE table. It's not going to make any difference, but initially I don't have anything yet dissolved. Now, after dissolving the change, I'm going to get S, and I'm going to get 2S here. And at equilibrium, it's going to be 0 plus S, so it's S. And here, 0 plus 2S, so again, it is 2S. So what do they want in this question? Assuming equilibrium is established between solid and dissolved CaF2, and that there are no other important equilibria affecting its solubility, calculate the solubility. But this time they want it in gram per liter. So I'm going to do exactly the same thing I did up in here by calculating solubility, but I will convert it eventually to gram per liter. So again, I begin with the expression of KSP, which is calcium multiplied by fluoride square. I'm going to substitute with S, and it's going to be 4S cubed. Now I already have the solubility product given in the question, 3.9 times 10 to the power negative 11. Therefore, S is going to be cubic root of 3.9 times 10 to the power negative 11 over 4. And that is equal to 2.1 times 10 to the power negative 4 molar. So, how do I converting S in molar to S in gram per liter? All I need to do is get the molar mass of CaF2 from the periodic table. So in the periodic table, calcium molar mass is 40 and the fluoride molar mass is 19. I'm going to show you. You see, here is the periodic table. The larger number is the molar mass, and here is F. The larger number is the molar mass. So if I add 40 and 19 twice, I get a molar mass of 78 gram per mole. So let's put the numbers here together. 2.1 times 10 to the power negative 4 mole per liter. I will multiply it by the molar mass, which is in gram per mole. Mole and mole, they cancel out. So we get our answer in gram per liter. So it's 1.6 times 10 to the power negative 2 gram per liter. Differentiate among unsaturated, saturated, and supersaturated solutions. So the saturated solution, it means that the solution is full. It cannot take any more solute to dissolve it. And when we have a saturated solution, it is in equilibrium, dynamic equilibrium with the solid. So first of all, it is a solution that has the maximum amount of solute dissolved, solute particles dissolved in the solvent. All the time the solvent is water. Now, how do I know that a solution is saturated? If I have a cup with water, I will not see anything because all the solute is dissolved. How do I know that this solution is saturated? If I add more solute, the solute is gonna deposit at the bottom, showing that it cannot take any additional solute to dissolve it. So if you add more solute to this saturated solution that is already at equilibrium, the particles of solute will appear. The particles of solute will appear as they can't dissolve. The solution is full, it's saturated, it's in dynamic equilibrium. It cannot take up more. Now, unsaturated solution, it means that you can still add more solute to dissolve it. So the solution can still dissolve more solute in it. It did not yet reach the dynamic equilibrium. So we call it unsaturated. So if I have the solution and I added more solute, I will not see here solute deposited at the bottom, while here I'll see more solute. Okay, so in the definition, in the answer key, it's written a solution containing less than the equilibrium amount of solute. It means it didn't take the maximum amount of solute that it can dissolve. I can give you in numbers. Like for example, a solubility of a solution is 2 grams per 100 milliliter. So if you added 1.5 grams in 100 milliliter, the solution is unsaturated because you can still add up to 0.5 grams. But in the saturated, if the solubility is 2 grams and you added 2 grams already, then it is saturated. Now, the supersaturated solution. A supersaturated solution is a solution that is unstable, like the solute in it is forced to dissolve, and if I put some additional solute in it, it will crystallize. it will crystallize. So I'm gonna just write here, under certain conditions, maybe elevated temperature, a super saturated solution contains solute more than the allowed amount at equilibrium, more than the allowed amount of solute that it can usually take, at equilibrium. And yet it is dissolved, probably because we increased the temperature. So we forced the solute to dissolve. Then when the temperature comes back down, the solute doesn't appear. It doesn't show immediately. Not until we add more solute to it, then it will crystallize. Okay? So the supersaturated solutions are unstable, and the excess of solute normally crystallize, يعني it appears at crystals, crystallize if additional solute was added to solution. I'll explain it. I have here a solution, and this solution can take up to 2 grams per 100 milliliter. So I added 2 grams already, and the 2 grams are dissolved. But I kept on adding solute, and I raised the temperature. So this added solute dissolved. So it's already dissolved. So now this solution probably has 4 grams per 100 milliliter of solute that was forced to dissolve. Okay? Now, take out the solution and let it cool down. So if the temperature goes back to normal, the solute, those additional 2 grams, they're not gonna reappear unless a crystal or more solute was added to it, just a tiny drop. At that point, when a tiny drop of solute is added to it, the solution will crystallize in 1 second immediately. So that is a supersaturated solution. Now explain what happens what happens to the reaction if Q equal K. Now Q is when I have like a certain given concentrations, like for example, I have like the example that was given to me up, calcium fluoride solution. Okay, let's say the KSP product of calcium fluoride solution is equal to 3.9 times 10 to the power 11. Okay, and the solubility is 2.1. Okay, let's say in this one, they are giving me certain concentrations of calcium and the fluoride. They are giving me certain concentrations of calcium and of fluoride. Okay? So, if I calculated them and I'll get an answer, they are given to me. This would be called Q. It will take the same formula of K. Okay? So if I calculated them and I received or I got an answer that is larger than K, I would say that with those concentrations, a solid will precipitate. If I get an answer that precipitate, if I get an answer that says that this solution or this value will be less than K, it means no precipitate will form. Now, if they were equal to K, Q is equal to K, I would say that the solution is saturated and it is at equilibrium. What is the molar solubility? So they want us to calculate S in mole per liter because they said molar of calcium fluoride in a solution already containing 0.100 molar of LiF. Be careful, there is F here and there is F here. This is the effect of common ion. Note that here, whenever we have a common ion, solubility will decrease. It will be less. Now here they're not asking us if it's going to increase or decrease. All they want is to calculate how much this solubility is. So what I'm going to do, I'm going to use the ICE table. Again, as you can see, all these questions, they start by writing the equilibrium equation. So calcium and 2F minus. Now, initially, I don't have calcium, but I do have 0.100 molar of F minus. Now, when there's a change, I'm going to get S, and I'm going to get here 2S. So at equilibrium, it's going to be S, and here it's going to be the value plus 2S. Now here, S is very small compared to 0.01. So as we are solving, I'm going to ignore or cancel this S over here because it's going to be a very negligible value. So KSP is equal to calcium concentration multiplied by fluoride concentration square, which is equal to S and 0.100 plus 2S squared. Now this S over here, to make the calculations easier, I'm going to ignore it. So it's going to be 0.100 squared S. Okay? Now, having the KSP given to me, it should be given in the question. So the KSP, I'm getting it from the answer key, but the KSP is always given. Okay? So in the answer key here, it's given as 1.646 times 10 to the power negative 10. It is equal to 0.100 squared S. So S is equal to 1.46 times 10 to the power negative 10 over 0.1 squared, and that is equal to 1.46 times 10 to the power negative 8 molar. Okay, so here in this case, whenever I add a common ion, the solubility will decrease, the amount of AQs will decrease, and I will get more solid will appear. So as if I am telling you that the equilibrium will shift to the right. The solubility of compounds with containing basic anions will what? At higher pH. Here we are dealing with if a base is added. That's what higher pH means. And they can change the question later on in the exam and tell you at lower pH. At lower pH means if an acid is added. Before I answer this question, let me just give you the basic rules. So here's what happens to solubility. If acid is added, means lower pH. And what happens if base is added? And they will tell you in the question at higher pH. So let's clarify it. Usually in acidic medium, the solubility, you're gonna say either increase or does not change. So solubility increase or no effect. Now, when does it increase? So I'm gonna write it here. When does it increase? If the salt you have, if the salt contain a basic anion, the solubility is gonna increase. So if the salt contains a basic ion, the solubility is gonna increase. What do you mean salt with basic anion? And I mean like, for example, CaF2. Let's say just any example containing ions like carbonate, hydroxide. Like for example, in the first question we got I think MnO4, OH2. So this one we had here magnesium hydroxide, or here I have barium fluoride. So these contain basic anion. So for example, I'm gonna write here MnOH2 or barium fluoride, any basic anion. When you see, for example, in its Cn minus, etc. So if you see these basic anions in the salt and pH was lowered, meaning acid was added, the solubility is gonna increase. Now, when the solubility has no effect, the solubility will not change if an acid is added. If salt contain pH neutral anion, and for example CaCl2, that's neutral, Cl is neutral, or it has an ion like I minus or Br minus, etc. So these ions are pH neutral, and this point you will say that the solubility will not change. So again, if I have a salt and I'm dealing with lower pH, meaning acid is added, you're either gonna say solubility is more if that salt contain basic anion, or you will simply say it's not gonna change, the solubility is not affected. Now, what's gonna happen at higher pH if I added a base? Now, if the salt, so your answer here is gonna vary. You either gonna say increase, and in some cases it's gonna decrease. Okay, sorry, in most of the cases it's gonna decrease when a base is added, but in some particular cases, in some exceptions, solubility will increase. So let me start with when it's gonna decrease. So I'm gonna say when it's going to decrease. If the salt to which you are adding a base contains a basic anion, because you're adding a base over a base containing a basic anion, equilibrium is gonna shift to the left and solubility will decrease. Okay, so solubility will decrease. And I'm gonna give you examples. Let's say I have a salt, like for example, magnesium hydroxide. That's a basic anion, and I added a base, so equilibrium is gonna go to the left. Or for example, I have another base, calcium fluoride. That's a basic anion, so it's gonna go to the left, it's gonna decrease. So here the answer, the solubility will decrease. Now, what's gonna happen, or what are the exceptional case? Except, now, what happens if the salt has the specific, the below cations in it, like aluminium, I'm talking about aluminium hydroxide, or zinc cation, or lead, or chromium. When these ions are present in the salt, they react with this added base because they are amphoteric, and in this case equilibrium will shift to the right and solubility will increase. Okay, so again, if I have a base and if I have a salt and we added an acid, usually the solubility increases. Okay, if I added an acid, usually the solubility will increase. But if I added a base, usually the solubility will decrease. Upon the addition of a base, the solubility will decrease. So that's it. On to subtopic 3.1, which is thermodynamics. Define a spontaneous process and explain how thermodynamics is involved. A spontaneous process is a process that can naturally occur by itself, naturally occurs without any outside intervention. And I mean by without any outside intervention, for example, it doesn't need a battery, for example, it goes by itself. So no battery or electrical energy involved. That's an example. Okay? Now, thermodynamics, and to say if a process is spontaneous or non-spontaneous, it depends on two factors: the enthalpy and the entropy. So based on enthalpy and entropy, we can know if a process is spontaneous, if delta G came to be calculated and we got it as negative, or if the process is positive, so therefore we say the process needs outside intervention because it's not spontaneous. Which of the following defines a spontaneous process? Again, so it's not necessarily a reaction that occurs instantly. I can have a spontaneous process that is slow, like rusting of iron. It takes days. And it's a reaction that requires continuous input of energy. That is the definition of non-spontaneous. The answer is C. Spontaneous means a reaction that occurs without any outside or external intervention. What does the spontaneity of a reaction indicate? Spontaneity of a reaction indicates that a reaction can happen and it has enough energy to do work. So, does it indicate that the reaction is going to always be quickly or fast? Not necessarily. A spontaneous, as I mentioned, spontaneous process can be slow and can be fast. It indicates that the reaction is thermodynamically favorable, but not necessarily fast. the reaction will require a catalyst. No, that's not a rule. Some reactions can happen, are spontaneous, and can take place without a catalyst. And even if a catalyst is involved, it doesn't mean that the reaction is non spontaneous or a catalyst is an outside intervention. Not at all. And no, I can have a decrease in entropy and still the reaction to be spontaneous. Explain why the spontaneity of a reaction does not indicate its speed, because they are not related. The spontaneity of a reaction depends on the sign of delta G, whether it's thermodynamically favored or no. So if delta G is negative, that is spontaneous. But if delta G is positive, it is non-spontaneous. And the two factors that will affect the sign of delta G, we take them from this formula. So delta S and delta H. So it has nothing to do with the speed. It's irrelevant. Meaning if you used a catalyst or you did not use a catalyst, it's the same. It's not related to a favorability. Will a reaction that is thermodynamically favored, spontaneous, be a fast reaction? No, it is not related. So, favorability is not related to the speed of a reaction. Okay, so I can have a very slow reaction and yet the reaction to be spontaneous. Next, describe exothermic and endothermic reactions. Exothermic reaction is a reaction that releases energy, and the system releases energy to the surrounding. An exothermic reaction means when you touch it, the reaction feels hot. So the temperature of the surrounding will increase. Now, what does it mean a system or reaction is endothermic? It means that the system absorbs energy from the surrounding. And it means that the temperature of the surrounding is gonna decrease. Now I'm gonna explain something related to bond breaking and bond forming and potential energy. I need you to know that when two atoms are bonding together, so bond forming, energy is released. So when two or when a bond is formed, energy is released. And when a bond is broken, energy is absorbed. So how do we think about this? Or in other words, when two atoms are forming a bond, usually it lowers their potential energy. They become more stable. Or when a bond is broken, the potential energy will increase because they become less stable. So let me just explain this. In an exothermic reaction, when a reaction it occurs, there are bonds to be broken and there are new bonds to be formed. So that's the norm. In this case, here, when bonds are broken, energy is absorbed. But when new bonds are formed, energy is released. But for the system to be exothermic, apparently here, the energy released must be more than the energy absorbed. Therefore, the overall is going to be exothermic. And here we say that the, the bonds of reactants are weaker than the bonds of products. That's what it says. And if I draw a diagram, here's the exothermic. You see, the energy formed will have lower potential energy. Look at the level of the line. They are more stable. And the energy of the reactants, they have higher potential energy. So here I have reactants, here I have products. So the potential energy of reactants in exothermic is higher than the potential energy of products. That's first. Second, the energy absorbed to break the bonds of reactants is less than the energy released to form the bonds of the products. And this means that the bonds of reactants are weaker than the bonds of products, because more energy was released to form the products than the energy absorbed to break the bonds in the reactant. Now it's the opposite in the endothermic. If I draw a diagram in the endothermic, it's going to be like that. I have here reactant and I have here products. Apparently, the energy absorbed to break the bonds in the reactants is more than the energy released. I'm gonna remove this because it might confuse you. So it's more than the energy released when bonds were formed. That's in the endothermic. And that is because the bonds of reactants are stronger than the bonds of products. And moreover, the potential energy of reactants is less than the potential energy of the products, meaning the reactants are more stable than the bonds of the products. Again, what does each diagram represent? This diagram here, I have a potential energy of reactants lower than the potential energy of products. Or you might say enthalpy of reactant is less than enthalpy of product. If you look at delta H is final minus initial. If you look at this one, the enthalpy of product is a higher number than the enthalpy of reactants. So if we calculated the value of delta H, we get a positive value. It means that this is an endothermic reaction diagram. Energy absorbed is a lot more than the energy released. The energy absorbed to break the bonds between reactants is a lot more than the energy released to form the bonds between the products. Okay? Now I just want to point at the energy absorbed is also called the activation energy in this case. From here till here, that's the activation energy to initiate this reaction and start the process of forming the bonds in the product. Now when I look at this diagram, I have potential energy or enthalpy of reactant higher than the enthalpy of products. If I calculated delta H, it's going to be final minus initial, and the value of product is less than the value of reactants, so the answer is going to be negative. Therefore, this diagram represents the diagram of an exothermic reaction. Moreover, the energy absorbed to break the bonds of reactants is a lot less than the energy released to form the bonds between the products. Define entropy. Entropy is a state function here. Is it a state function? Yes. I'll explain this in a minute. So entropy, it's the degree of randomness. It measures the degree of randomness of a system. So, for example, if I have a system that is solid, so the particles are arranged in a perfect arrangement, so that is solid. If I am comparing it to a gas, the randomness here or the chaos is more. So entropy, it's this randomness. It measures the degree of disorder of a system, how much a system is disordered. Disorder of a system. Now, is entropy a state function? Yes. What do I mean by state function? State function means we don't care what happens in between. We only compare the initial entropy, like entropy initially, with final entropy. What was the system before and what happened to the system after. It doesn't matter what happened in between. So it means it's a state function. Now you need to know that the unit of entropy is in joules per Kelvin. Moving on. Which of these processes result in entropy being positive? An entropy to be positive, it means that the randomness or the disorder increased. Let's look at these two equations here. They are comparing this one to this one. Here I have gas and it's still gas, but I have 2 mole versus 3 moles. So the amount of particles or moles of molecules increased. So there is an increase in the entropy. Entropy is going to be positive. Let's look at this one. I have solid and gas, but now in the product, I only have solid. And solid has less entropy than gas. Plus, I have 2 moles versus 1 mole. So the delta S here is negative. So this is the answer, this one. Now let's look at the other one. A change from solid to gas, entropy is going to be positive. Whereas a change from liquid to solid, there is more order, less randomness. Entropy is going to be negative. Moving on, expect questions when they give you to compare between two substances, different states. So, which one has higher entropy? Of course, the gas. The gas will have higher entropy because the molecules in gaseous state, they move randomly and freely with more disorder compared to liquid. Okay? Now, CO2 gas and O2 gas. Now, these two compounds are both gas. So, we're going to look at the molecule complexity. So, which molecule is more complex? CO2. So I'm gonna choose here CO2 gas because the more complex the molecule, the more type of vibrations and so the more complex the molecule is, the more options for motion and movement and vibrations and translational motion, so of vibrations. Okay, so these molecules, they are going to move in more random ways than the O2. Identify 4 processes where entropy always increase. Okay, let's see. Any change from solid to liquid, entropy increase. So for example, I can say melting of whatever, melting of ice, melting of piece of metal, melting of iron, any melting process. Or any change from liquid to gas. So you're gonna say any evaporation process increases the entropy. So you can say ammonia, liquid ammonia evaporates, you can say water evaporates, any change of state from liquid to gas. Or, for example, if I have a solid solute like NaCl, salt solid, and I am dissolving it in solution in water to become aqueous, So any change from solid to aqueous, entropy increase. Or, for example, if I have a gas that is a solute that is dissolved, like aqueous, like for example, a bottle of sparkling water, for example, it will have CO2 dissolved in it, or for example the oxygen dissolved in water inside a fish aquarium. Now if this bottle is opened, then the carbon dioxide gas is gonna escape in form of a gas. So any change from aqueous to gas involves an increase in entropy. Or for example, if a process involves formation of more particles than it was in the reactant, that's an increase in entropy. Or for example, if temperature increase, entropy increase. Mixing involves increase of entropy. A reduced pressure on gases also involves increase in entropy. Which one has higher entropy? Iodine solid or gaseous iodine? Of course, the gaseous iodine, because the molecules in gas are more free to move. In solid, they just vibrate in place. They don't move. Here, they move freely, randomly. So there is more entropy. On to the questions covering subtopic 3.2. In this subtopic, you have the KPIs included is to state the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. So I'm just going to mention the 3 of them. The first law of thermodynamics states that energy is never lost. Energy cannot be created nor destroyed. It's just changed from another form to another form. So can be converted from one form to another. So nor created, neither destroyed. That's the first law. Now, I think there's a question here about the second and the third law. No. So let me just state the second law and the third law. So the second law of thermodynamics states that, second law, entropy is always increasing. Entropy of the universe. That's it. Entropy is always increasing. And for the third law, it states that the entropy of a perfect crystal is 0. S equals 0 for a perfect crystal. So these are the laws. So if it comes, you know what to do. Write the relationship between entropy of surrounding. So entropy of surrounding and the enthalpy of the reaction, like delta H of the system, or you can also call it delta H of reaction with units. Then predict the changes in the entropy of the surrounding for exothermic and endothermic at constant pressure. So to begin with, the formula of delta S entropy of surrounding is minus enthalpy of a system or of a reaction over the temperature. Now note that the enthalpy unit is always in kilojoule. It could be positive and it could be negative. And the temperature is in Kelvin and it's always positive. Now entropy of surrounding in this case is going to be joule per Kelvin. Now let's say I have an exothermic system. So in an exothermic system, delta H is going to be negative. So delta H is less than 0. So in this case, entropy of surrounding, you have here a negative value, then enthalpy is negative over a positive value. The answer is going to be positive answer. So in this case, entropy of surrounding is increasing. In the case of an endothermic system, the enthalpy of the system is positive. So if I put any value into this formula, there's a minus in the formula, there's the enthalpy is positive and temperature in Kelvin is already positive. So the answer here is going to be a negative value. So in this case, the entropy of the surrounding is decreasing. It has a negative value. Why does a negative delta G indicate a spontaneous process? Delta G means the energy available to do work for a process to happen. Okay, so it's the energy available to make the process thermodynamically favorable and spontaneous. So if delta G is negative, it means there is a free energy, there is a release of energy, of a free energy to let, or in order to make the process, to allow the process to be thermodynamically favored. Explain the thermodynamic favorability for a system with a negative entropy and a positive delta H. So, if I'm just gonna put this formula, delta G equal delta H minus T delta S. Okay, and I'm gonna give you all cases. So like this, you can remember it, and I will also explain this one. Okay, so let's put here delta H and delta S. When both of them have opposite values, and if I plug them into this formula, here, for the first case, for an exothermic reaction with an increasing entropy, the system is forever spontaneous. No matter what the temperature is, delta G is always going to be negative. When we calculate delta G is always going to be negative. So if you plug a negative value here and a positive value, the answer is going to always be negative. Now, what if I have an endothermic reaction with a decreasing entropy? In this case, the system is never going to be thermodynamically favored, so it's never spontaneous, and the delta G in this case is always positive. Now, when the system is spontaneous depending on temperature is when delta H and delta S have the same signs, like if both of them are positive or if both of them are negative. So if both of them are positive, delta G will be negative only if temperature is high. So they are favored, the system is favored only when temperature is high. And when both of them are negative, like the question here is asking, when both of them are negative, this reaction can be spontaneous, thermodynamically favored only at low temperatures. So you need to memorize this table very well. Now, the standard entropy of a reaction is calculated. How do I calculate the standard entropy? There's the summation equation. Delta S of a reaction is equal to the entropy, the sum of entropy of products. Now, of course, if a product is multiplied by stoichiometric coefficient, you need to multiply its entropy by that coefficient minus the sum of the entropy of reactant, of course, multiplied by the stoichiometric coefficient. So let's take this example and solve to calculate the delta S of the reaction. In here I have this is the equation. Over here, they're giving me the entropy of hydrogen and the entropy of oxygen and the entropy of H2. So I'm just going to give you a very simple way in order to get this done. So we put here, we can substitute like in the formula. So 2 multiplied by hydrogen is 130.7 plus the one of oxygen is 205.2, and I have here 2 times the one of water, which is 69.9. Now if I calculate this, each value, I'm gonna get 466.6, and this one is 139.8. Now the delta S of a reaction is the entropy of products, so this side 139.8 minus the entropy of reactant, which is 466.6, and the answer is minus 326.8 joule per Kelvin. Let's take another example. Use the table below to answer the questions that follow. Now here the table is a bit shifted. So here's delta H. All of those are enthalpy of formation values. All of those here are Gibbs free energy of formation. And here the entropy of each value. Note that, oh, there's more here. Note that entropy is never zero, but the Gibbs free energy and the enthalpy of formation, they can be equal to zero if the element is in the standard form. Like look over here, when I have carbon in the graphite, it's zero for H of formation and G of formation, but it's not zero for the entropy. Same thing here for hydrogen in the standard state. These two values can be zero, but the S can never be zero. Now let's calculate in here. Delta S for the reaction is, so I'm gonna take the product of S, which is this one, 219.4 minus the one of the sum of the reactants. I have hydrogen 130.58 plus C2H2, which is 200.8. So the final answer is going to be 112. I'm not sure if the answer is correct in the answer key. 219, and C2H2 gas is 208. So let me get the answer here. So the value here is, I'm gonna solve it up in here. So for this one is 331.38, and for C2H4 it's 219.4. So the answer is 219.4 minus 331.38. The answer is negative 111.98 joule per Kelvin, per mole Kelvin. Okay, I think there's a mistake in the answer. So in the answer key, they wrote it as positive. It should be negative. Now, what is the entropy of oxygen gas in the reaction below? So here again, I have the value. I have the entropy of the reaction already. So I'm going to write the equation. Entropy of reaction is entropy of products total minus entropy of reactants. So since this value is given, we're going to plug it here. Product is for H2O, which is 70, minus reactant, I have half O2, which is unknown, plus the hydrogen 131. So negative 163.5 minus 70, I'm going to take it to the other side, plus 131, you know this is minus, but when I take it to the other side it goes back again to be positive. Now let me do those calculations just to make sure that I have the right answer. Minus 70 plus 131. So that is negative 102.5 equal negative half, minus they cancels out. So the entropy of oxygen is going to be times 2. Yes, that is correct. Joule per mole Kelvin. Moving on to calculate the delta G using like following Hess's law, like a sum of several reactions, and then we can calculate the delta G. So here we have to follow a method. You look at the reactant and products and you find them in the given equations. So I'm going to name this equation A and this B, and this equation I'll name it as C. Now I'm going to look for carbon that I have over here. I'm going to find it in the equation. I find it in C, in B, sorry. I need it to be a reactant. It's already a reactant. But I need it to be multiplied by 3. So I'm going to say multiply equation B by 3. And I'll write it 3C plus 3O2 gives 3CO2. In this case, when we do this one and we multiply it by 3, we get negative 394.4 times 3. So the answer is going to be negative 1183 kilojoule. And I'm done with this equation. I'm not going to use it again. Now I'm going to look for hydrogen. I'll find it in equation C. And I need it to be 4 instead of 2. So I'm going to multiply equation C by 2. So 2 times 2, that's 4 hydrogen plus 2 oxygen. And then 2 times 2, that's 4 H2O. And again, this negative 457.1 is going to be multiplied by 2. And that is equal to negative 914.2 kilojoule. And I'm done with this one. Now I'll find this in A. It has to be the same. So A stays the same. And I'll copy it again. Wait, sorry. So I need this to be in the product side. So I need to flip A. So in this case, these are going to be the reactants. 3CO2 plus 4H2O. And I'll obtain C3H8 and 5O2. And in this case, because I flipped the equation, delta G is going to be 2074 kilojoule. Once we are done, we're going to add all the values of delta G. Now 3CO2 and 3CO2 will cancel out. 5O2 and here 5O2 will cancel out. And 4H2O and 4H2O will cancel out. So I'm left with the original equation that I want to calculate its delta G. And delta G of this system is going to be negative plus this value. I'm going to take those numbers. So the final answer is going to be negative 23 kilojoule. Again, calculate the Gibbs free energy, the standard Gibbs free energy at 298 Kelvin. And it's given, I have the delta H, and I have the entropy, and I have the equation. So there's also another way to calculate delta G, and it's by using this formula. All of these formulas are found in your formula sheet. So it is delta H minus T delta S. Be careful to the units. So delta G is going to be in kilojoule per mole. Delta H is already in kilojoule per mole, so I don't have a problem in converting it, and I have to keep it the same. Minus. Now the temperature is 298 Kelvin. Don't forget to use parentheses here. And the delta S has to be 163.2. Now look at this. The unit is joule per mole and I want it in kilojoule. So you are going to divide this, convert it to kilojoule. And the final answer is going to be negative 532.2 kilojoule per mole. Now the value of this delta G is negative. Therefore, this reaction is thermodynamically favored. It is spontaneous. Now, again, calculate the Gibbs free energy, delta G, for this reaction at 25 degrees Celsius. I have a delta S, H, and delta S given. Now look at the value of delta H. Delta H is negative, exothermic, and delta S is positive. So my expectations is to have a negative delta G, because in exothermic and increasing entropy, the reaction is always favored. Same thing also in the previous question. So let's plug the values. Delta G is equal to delta H minus T. I'm going to add this to 273. So it's going to be 298 Kelvin multiplied by delta S, that I should not forget to convert it into kilojoule. So the final answer is going to be negative 22.68 kilojoule per mole. And the answer key, they're forgetting to write per mole. So don't forget that in your calculations when you are writing your answers. Differentiate between delta G standard and actual delta G, or delta G under non-standard conditions. So as I said, this one is under standard conditions. This is the Gibbs free energy under standard conditions, and this one under non-standard conditions. Now I'm just gonna mention to you the standard conditions so that you'll understand what do I mean. So standard conditions, if I have solutions, their concentrations of reactants and products, of reactants maybe, it's gonna be 1 mole. If I have aqueous solutions reacting together. Now if I have a reaction of gases, in their standard conditions, their pressure must be equal to 1 atmosphere to be considered in standard conditions. Now, if I have solids and liquid, they must be in their pure state. Under non-standard conditions, the concentration is not 1 molar, and the pressure of any gas present is not 1 atmosphere. Now let's continue. Tabulate the relationship between delta G standard and delta G non-standard and explain the mass action ratio we mean by this Q. Now Q takes the formula of K, and it is the actual ratio of product over reactant. So if you have the pressure of products, you divide it, you raise the pressure to the stoichiometric coefficient, and you divide it over the pressure of reactants. If you have concentrations, you do the same. You always do not include in the formula of Q anything solid or liquid, not to be included in the formula of Q. Now, what else? Now, delta G and delta G standard. Standard is at standard conditions, and delta G is the actual when the conditions are not standard. Now we have this formula. Like the deviation, it's delta G standard plus RT ln Q. I use the Q because I'm dealing with delta G at non-standard conditions. Now in standard conditions, instead of using Q, I'll be using K. Now what does this mean? So let's take first if Q is equal to 1. So let's say if Q is equal to 1, what does that mean? If I plug this into my calculator, ln 1 is going to be equal to 0. And 0 multiplied by RT will give me 0. And in this case, delta G is equal to delta G standard. So at this condition, delta G and delta G standard are equal to each other of the reaction. Now, let's continue. At equilibrium, so here this one, I'm just gonna write it. At standard conditions when Q is equal to 1. Now, at equilibrium, delta G is equal to 0. And I'm gonna explain this when I reach this graph over here as well. So delta G is equal to 0. Therefore, in this case also at equilibrium, Q is equal to K. So if I substitute into this formula, so this is equal to 0, and this is delta G standard plus RT ln, and I just said that Q equal K, so I can use K, and therefore if I take this value over here, I'm gonna get delta G standard reaction equal minus RT ln K. This formula is present in your formula sheet. So that is at equilibrium. Now, under non-standard conditions, delta G is not equal to delta G standard. Therefore, the reaction direction depends on Q compared to K. So if Q is less than K, the reaction is gonna proceed toward the equilibrium, is not yet reached equilibrium. Or if Q is more than K, it means that the reaction passed equilibrium. So this one will tell you what's actually going on. So in general, at non-standard conditions, we use this formula, delta G standard plus RT ln Q, and we calculate Q and we will know where the reaction stands. Now, in the next question, use the swing curves below to describe the spontaneity of reaction based on the sign of standard free energy and the value of equilibrium constant K. So the sign of delta G and K. Now let me first explain this graph. Whenever you see a graph like this, I want you to draw the y-axis also from the other side of the graph. Now the x-axis represents the progress of the reaction and the y-axis represents the Gibbs free energy. Now, whenever you look at the graph, this point, the starting point is the Gibbs free energy of reactants, and the last point of the graph is where is the Gibbs free energy of products. Now I want you to look at the value of G reactant and the value of G product. If we calculate delta G, it is G product minus G reactant. It's always final minus initial. And in this case, because the product's Gibbs free energy is lower than the reactants, the value of delta G is always going to be a negative value. In this case, we say that this reaction is spontaneous. Now I'm going to give you another example. You can remember it all the time. If you have a marble and you place the marble on top of this curve and you let it roll, this marble is going to roll down and eventually stops here. Now this swing over here, this curve over here, it can tell you at any point of the graph whether the reaction is spontaneous or non-spontaneous or at equilibrium. At this point here, we say that the reaction is at equilibrium and delta G is equal to 0. Now, any point on this graph, like if I take this point, since the marble is gonna roll down, it means that this reaction is product favored. Product favored, which means it is spontaneous because the reactant are going toward giving the product. When the marble reach here, it means we reached an equilibrium state, and at this point G is equal to 0. We are at equilibrium and there is no more energy to drive a reaction. Now, of course, if I have a point or a marble at this point, it's gonna roll back. It means the products are going backward for the reactants. Now, in general, when you look at a graph like this, a swing shifted to the right, you just have to remember the point of product lower than the point of the reactants. So final minus initial will always give me a negative value. And if a reaction is favored, then definitely K is larger than 1. And this is what they ask in the question, to predict the sign of delta G and the value of K. Now let's look at the other graph. Again, draw the y-axis. Here's the point of the product and here's the point of the reactant. Now if I want to calculate delta G, it's the product, a higher value, minus the reactant, a lower value. At this point, our answer is going to be positive. And again, if I put a marble over here, this marble is gonna roll down. It means the products are favored like in the direction of reactants. So the product are more favored to give the reactants. So this means this swing shows a reaction that is reactant favored. Or in other words, you see, this is reactant favored. So it is non-spontaneous because delta G is positive. Whereas this one is product favored. So it's like that in the direction. Now, of course, if delta G is positive, in this case, K is gonna be very low and I have more reactant than I have product because the products are more favored in giving the reactant and not the opposite. Now let's move to subtopic 4.1. And here we start with with electrochemistry. Balance the reaction in acidic medium. Now I'm gonna need a bit of space, so I'm gonna use this space here above in order to do the balancing in acidic medium, and I'll go through the steps step by step. So first of all, when you have the equation given, you split it into two half equations. So NO3 minus nitrate giving the nitrogen dioxide. First of all, you look at any atom other than oxygen and hydrogen to balance them by adding coefficients. So here I have 1n and here 1n. So nitrogen atom is balanced. So first, balance any atom that is not O and not hydrogen. And by the way, you can look at the video on my channel to follow exactly the steps. Now the next step is to balance oxygen atom by adding H2O on the side that needs more oxygen. So here I have 3 and here I have 2. So this side we have one more oxygen missing. So we're gonna add 1 H2O. Now, next we balance hydrogen by adding H plus on the side that is missing hydrogen. Now here I have 2 hydrogens, so I'm gonna add here 2 H pluses. After you balance the oxygen and the hydrogen, you move to balance the charges by adding electron on the side that has higher charges. Now this side here is zero, neutral. There's no charge here and no charge here. So on product side, the charge is zero. Whereas on the reactant side, I have a minus here and I have two pluses. So the overall charge is +1. Now this side is the side with higher charge. So I'm gonna add electrons to it until it reaches or equal the other side. So until it equals 0. So 1 electron needs to be added. And here we go. We balanced the first one. Now, again, I minus iodide. I need to balance it with IO3 negative. So, 1I already balanced. 3 oxygen, so I'm gonna add on the side that is missing oxygen 3 H2O. Remember, you balance O by adding H2O. Now, how many hydrogens now I have? 3 times 2, that is 6. So I add H plus on the side that is missing hydrogens. Now I have to calculate the charges. On this side, I only have 1 minus. So 1 minus is this charge. Here I have 1 minus and 6 pluses. So the overall is 5 pluses. So here's the side that is higher in charges. And I need to add electrons on this side until it reaches -1. If I added 5 electrons, it's going to be 0. So I better add 6 electrons. So both sides of the half, for both sides of this half reaction are equal to -1 in charge. Now, 1 electron in here gained and 6 electrons lost. So we need to multiply this half equation by 6 to balance the electrons lost and gained. Finally, I'm going to write it over here. So 6 electrons plus 6 NO3 minus plus 6 times 2, that is 12 H plus. Now I move on here, plus I minus, and 3 H2O. I'm done. Now 6 NO2 and 6 H2O and IO3 minus and 6H plus and 6 electrons. 6 electrons, 6 electrons, they cancel out. 6H2O and 3H2O, I only have 3H2O remaining. Now 6H plus and 12, I have 6H plus remaining. Now I'm gonna copy it here. 6NO3 minus plus 6H plus gives 6NO2 and 3H2O and IO3 minus. Please don't forget the physical states. Now in here it's not written, but in your exam it will be given, so you just copy them as they are. What is needed to balance it in basic medium? Now what is the step to do if I need to balance it in the basic medium? The basic medium is exactly the same steps we follow, but when we reach the end, we look at how many H plus we have, and we add equal amounts of OH minus on both sides. So here I have 6H plus, so I'm gonna add 6 OH minus in here and 6 OH minus in here. So how much is needed to balance it in acidic medium? We need to add 6 OH minus on both sides. Now I'm gonna show you what's gonna happen. Plus 6H plus and 6 OH minus plus I minus gives 6NO2 plus 3H2O and IO3 minus and 6OH minus. Now note that every H plus and OH minus added together, they give me H2O. So from those here, I'm just going to get 6H2O. And IO3 minus and 6OH minus. So now I can cancel the H2O here, and this 3 remains. So now if I look at this equation is now balanced in basic medium. In here it was balanced in acidic medium because I see H plus in it. Balance the following redox reaction if it occurs in acidic solution, and what are the coefficients that I should add here and in front of H2O. So again, let's split this out into two equations. MnO4 minus 2 Mn2 plus. So in this one, I have 1 Mn, 1 Mn, 4O, so I'm gonna add 4 H2O because we balance O by adding H2O. Now I have 8 hydrogens, so I'm gonna add 8 H pluses, and now I'm gonna calculate the charges on each side. Here I have 2 plus, and here I have 8 plus, don't forget the number next to H plus, and 1 minus, so here I have 7 plus. As I said, we add electron to the side that has higher charge because we want to lower it to equal the other side. So if I have 7 pluses and I added 5 minuses, 5 electrons, the charge on both sides is going to be 2 plus. Moving on. The second half equation is H2 C2O4 giving CO2. Now, of course, in every half reactions you write, one is always going to be reduction, the other one is going to be oxidation. Like in here, reduction, oxidation. Again here, in this one, this is reduction, so I expect the other one to be oxidation. So first I'm gonna start with atom that is not oxygen and not hydrogen. So I have here carbon and here 1 carbon. So we balance the atoms by multiplying them with the stoichiometric coefficients. Next, we move to balancing oxygen by adding H2O on the side that is missing O. 2 times 2, here I have 4 oxygen. And here I already have 4 oxygen. So this is balanced for O. So there's no need to do anything. Now I have 2 hydrogens. I'm going to balance the hydrogens by adding H pluses. Now I'm going to move on to charges. Here the charge is 0 and here the charge is 2 plus. So I'm going to add 2 electrons to make them equal. Now, when I want to add both, this is 5 and this is 2. So I'm going to multiply this by 2 and here by 5 to make the electrons transferred equal to 10. So 2MnO4, I'm just going to write it over here. 2MnO4 minus, and wait, I'll do it here and then I'll write the final one over there. 2MnO4 minus plus 16H plus 10 electron. I'm done with this side. Now 5H2C2O4, I'm done. Gives 2Mn2 plus and 8H2O. 5 times 2, that is 10 CO2 and 10 H plus and 10 electrons. Now we start cancelling out the electrons. I have 10 H plus here and I have 16. 6 will remain and that's it. So I have 2MnO4 plus 6H plus and 5H2C2O4. This is gonna give me 2Mn2 plus and 8H2O and 10CO2. So the question was, what are the coefficients for H2C2O4? It's gonna be 5, and for H2O is gonna be 8. Next, another example, but this time in basic solution. So let's begin. I don't know, I have a feeling that in the exam it's gonna be the balancing in basic solution, because this time they're stressing a lot on balancing in basic. So let me just break this into two equations. Now here you can see I only have one reactant, so I'm gonna use it twice. One time to say Br2 gives BrO3 minus, and the other time is I'm gonna say this gives Br minus. Let me first finish the first one. I start balancing atoms that are not oxygen and hydrogen. I have 2 bromine, so I'm gonna add 2. Next, I move to oxygen. I have 3O, so I'm gonna add here 3H2O. Now I have 6 hydrogens, so I'm gonna add here 6H pluses. Now I'm gonna count the charges. Don't forget the charges. Here I have 2 minus and 6 plus, so I have a total of 4 plus, and here is 0. So that's the higher side of charge, and I want to make it 0 because here I have 0. So I'm gonna add 4 electrons, and I'm done with the first one. Now moving on to the second. Again, Br2 giving Br minus. Now 2Br, here's 2Br. Now this side 2 minus, and here's 0, so it's higher. I'm gonna add 2 electrons to balance them. Now the overall. Here I have 4, and here I have 2. So I'm only gonna multiply this side by 2, and like this I'll have 4 electrons gained, 4 lost. So Br2 from here plus 2Br2 from this side, and 3H2O and 4 electrons. So I'm done here and here. Now 2Br03 minus and 6H plus and 4 electrons, and 2 times 2, that is 4 Br minus. Now these Br2 and Br2, I'm gonna add them together, and it's gonna be 3 Br2. Now H2O doesn't cancel, 3. 4 electrons and 4 electrons will cancel out. Now I have 2 Br03 minus and 6H plus and 4 Br minus. That's the final answer. Now, again, I almost forgot. They want it in basic. So in basic, I'm not done. I need to continue. So I look at H plus. How much H plus I have? I have 6. So I'm gonna add to this side 6OH minus, and to this side 6OH minus. Now 6H plus 6OH minus will give me 6H2O. So I'm gonna write this again. 6OH minus and 3Br2 and 3H2O, 2Br03 minus. Now those two, I'm gonna put 6H2O and 4Br minus. Now 6H2O, 3H2O will cancel out, and from those 6, 3 remains. So the question was, what are the coefficients instead of in front of Br2? It is 3, and in front of OH minus, it is 6. Again, another question in basic medium. So in this one, this goes to this and here to this one. MnO4 minus giving MnO2. 1 Mn, 1 Mn. It is balanced. Now I move to oxygen. 4, here I have 2. So I have 2 missing oxygens, so I'll add 2 H2O. Now by doing this, now I have 4 hydrogens. So I'm gonna add here 4H plus. Now I have 4 pluses here. Don't forget to see the 4 and multiply it. 4 pluses and 1 minus. So it is 3 plus versus 0. So this is the higher side with charge. I need to make it equal to 0. So I'm gonna add 3 electrons to the 3 plus. Next, NO2 minus giving NO3 minus. 1N, 1N, balanced. 2O, 3O. So I have 1 oxygen missing over here. Now, I have 2 hydrogens. So I'm gonna add 2 H pluses over here. Now let's count the charges. 1 minus and 2 plus, that's a 1 plus. And here, 1 minus only, that's neutral, so 1 minus. This is the higher side with charges. I want to add electrons to make it equal to -1. So if I add 1 electron, it's going to be 0. But if I add 2 electrons, it's going to be -1. And again, this is a reduction, and this I got it as an oxidation. So I'm good. Now, I'm going to add both of them. Here I have, I'm just going to change the color a bit. So here I have 3, and here I have 2. So I'm going to multiply this by 2, and this by 3. And now I'll copy it. 2 MnO4 minus plus 2 by 4, that is 8H plus, 2 by 3, that is 6 electrons. I'm done with this side. Now I'll move here. 3 NO2 minus, 3 H2O. I'm done here. Now, two MnO2 and 2 times 2, 4 H2O, 3 this one, and 3 by 2H plus, that's a 6H plus, and 6 electrons. Now let's see what we can cancel out. 6 electrons, 6 electrons. 3H2O, 4H2O, 1 will remain. H plus, 6H plus, and 8, 2 will remain. And I think that's it, but I should not forget that this is in basic. So I'm going to write it 2 MnO4 minus plus 2H plus and 3 NO2 minus giving 2 MnO2 and H2O and 3 NO3 minus. Now we look at how many H plus we have. We have 2 H plus. So I'm going to add 2 OH minus here and 2 OH minus over here. Now let's write it. 2H plus and 2OH minus is going to equal to 2H2O. So I'm going to write it again. 2 MnO4 minus plus 2H2O plus 3 NO2 minus will give me 2 MnO2 and H2O and 3NO3 minus and 2 hydroxide ion. Now this is gone and only this one will remain. And the final answer is 2MnO4 minus plus H2O and 3 nitrite MnO2 3NO3 minus and 2OH minus. Be careful because here it's a bit confusing. There's an Mn and there's an N, there's NO2, there's NO3. So please be careful when you are doing this and the charges. So I balanced this in in basic medium. Again, one more question. Given the following redox equation, write the reduction, then write the oxidation, then put the overall. Now, I don't have to know everything from the beginning, but I can look at Fe going to Fe3 plus, and I see that this was oxidized. So I'm going to write this one over here. And definitely the second one is going to be the reduction. So I'm going to add 3 electrons. I should not forget the physical states. And now MnO4 minus giving Mn2 plus AQS and AQS. Let me see if I did something similar. Yeah, I did it over here. You see this MnO4 minus to Mn2 plus. So I'm just going to copy this one instead of doing it again. So plus 8H plus and 5 electrons. And here I have 4H2O. So now let's look at these two. I have 5 electrons gained and 3 electrons lost. So whenever I do this, I'm going to multiply this by 3. And I'm going to multiply this by 5. And I'm going to write both of them, the overall, over here. So 3MnO4 minus. I should not forget the liquid here. And the AQ here. Plus 3 times 8, that is 24. 3 times 5, that is 15 electrons. I'm done with this side. Now I'm moving to here. Plus 5 iron solid gives 3 Mn2 plus and 12 H2O and 5 Fe3 plus and 15 electrons. 15 and 15, they cancel out. Oh, this one is in basic. Now I have 24 H plus. So 15 and 15 cancelled out. Okay, there's nothing else to cancel. So I'm going to add 24 OH minus on both sides. And I'm going to write it again. So 3MnO4 minus and 24 H2O and 5 iron, 3Mn2 plus and 12 H2O and 24 OH minus and 5 Fe3 plus. Now 12 H2O, they cancel out, and out of those 24, 12 remains. So finally, I'm going to write it the last time with the physical states. So you must not forget the physical states. Fe is solid, Mn2 plus AQS, 24 hydroxide ion, and 5 iron 3 plus. How many electrons are transferred in the following reaction? So let's look at this one. This following reaction is not balanced. So I need to balance it and check the electrons transferred. 2 and 2 electrons. I'm not done yet. Now Fe to Fe3 plus, and here I have 3 electrons. And now when I see here 2 and I see here 3, I know that I must multiply this by 3 and this by 2. By doing so, we get 6 electrons lost and 6 electrons gained. Moving on with our questions. Question 41, define the electrical current. In your formula sheet, you have I equal Q over time. It's the charge per time. It's the charge in Coulomb per time in seconds. Now, as a definition, electrical current is the flow of the electric charge, of electric charge. Now, the current direction is opposite to the direction of electrons. Electrons, they flow from anode towards the cathode, whereas the current, it flows from cathode to anode. That's the direction of the current. Now, how current is generated? How is it generated in a cell? Since the redox reactions, the reduction and the oxidation occurring at the cathode and anode involves a transfer of electrons, involves a transfer of electrons, they can generate, this result in generating electric current. So with their voltage, an electric current is generated. Now, what is an oxidation half reaction? The oxidation half reaction happens at the anode, whether I have an electrolytic or a galvanic cell. It happens at the anode, while the other one, it happens at the reduction, at the cathode. Now, the main difference here is that the oxidation involves loss of electrons, whereas reduction involves gain of electrons. What is the difference between oxidizing agent and reducing agent? So I'm just going to give an example. If I have an oxidation of zinc solid going to Zn2 plus aqueous plus 2 electrons, we say that zinc got oxidized. The substance got oxidized. So this is the one that will be called a reducing agent. So the reducing agent is the substance that undergoes oxidation or undergoes a loss of electrons. Loses electrons and undergoes oxidation. Now let's do the opposite. If I have, for example, Fe3 plus electron going to Fe2 plus, that's a reduction from 3 plus to 2 plus. So Fe3 plus got reduced. So this is the substance that I call oxidizing agent. So is the substance that gains electrons and undergoes a reduction. What is meant by redox reaction? You see, when you read the word redox, it involves the half equation of the half reaction of oxidation and the other half of reduction. So together, when we add them together, because a reaction cannot be only loss of electron or only gain of electron, they have to occur both together. One part loses, one part gain, so that they form a full complete equation of redox. And that's why we call each one a half equation and the other half, because they make one full reaction. So a redox reaction is a reaction in which reduction and oxidation happens at the same time, occurs simultaneously. They involve the transfer of electrons. Moving on. What's the difference between a voltaic and an electrolytic cell? So let me make a table here and start writing the differences. So when we say voltaic, it means a galvanic cell, and electrolytic is the other type of cell. Now, first of all, the main important difference between these cells is the change or the conversion in energy. A voltaic cell involves a chemical reaction that happens and produces an electric current. So we say there's a transfer from chemical energy, there's a change from chemical energy to electrical energy. It generates an electricity. It generates electricity. Whereas in the electrolytic cell, we here need a battery for the chemical reaction to occur. It consumes the electricity to initiate a chemical reaction. So here there's a change from electrical energy into chemical energy. So this one requires a battery to operate, whereas this one, it is the battery itself. It gives us the battery. So it doesn't require a battery, a power source. So slash, I'm gonna say a power source to operate. Okay, now the next difference, a galvanic cell is a spontaneous cell. It's a spontaneous cell. The reaction that takes place there is a spontaneous chemical reaction. Whereas in the electrolytic cell, it involves a non-spontaneous chemical reaction. Okay? Now, another thing. When we calculate the E cell of a voltaic cell, it is always positive. When we calculate the E cell of an electrolytic cell, it is always negative. Now, also the delta G in a voltaic cell is negative. the delta G here is positive. Sorry, positive. Now also if I want to involve K, because K is included in our topic, it's above 1. Here it's gonna be less than 1. Okay, so here requires a device, the electrolytic cell requires a device to operate. It uses electrical energy to let the reaction start. The other one, it doesn't. Another important thing, a main difference between galvanic and electrolytic cell, anode in the galvanic cell is the negative electrode, and cathode is the positive electrode. Whereas in the electrolytic cell, anode is the positive electrode and cathode is the negative electrode. But where oxidation takes place and where reduction takes place doesn't change, which means in both anode of electrolytic cell and anode of galvanic cell, there is an oxidation taking place and there is a loss of electron. And cathode of electrolytic cell and anode of and cathode of galvanic cell, both of them, there is a reduction and a gain of electrons. Okay, so which cell uses a battery? The electrolytic cell. You have to know, or sometimes they will ask you which cell needs a device to operate. Or in the diagram, if a diagram is given to you, you will see on top of the electrolytic cell in the figure like a battery, written on it battery, or they might write on it power source, for example, power source, or you might see it probably I think like that. Now for the galvanic cell you will see a voltmeter. Okay, so that's the difference. Okay, let's continue. Which cell contains a salt bridge? It's definitely the galvanic, also known voltaic cell. Now, identify the parts of a voltaic cell and tabulate the differences between anode and cathode. Now, I tried as much as possible to bring a similar figure for the diagram represented. You will definitely get something like that in the exam, a cell to annotate or to indicate, for example, the direction of the ions in the salt bridge, or anything. It could be similar to this. Okay, now I want you to see that the E cell over here looks positive, so that's a galvanic cell. Okay, now on this one I'm just gonna write electron flow, and because the electron are going in this direction, okay, so this one would be the anode, so that would be the anode, and that would be the cathode. So down in here is the what we call the anodic solution, or I can say anode half cell solution, anode half cell solution, or anode compartment. What else? Anodic solution, I mentioned that. But or anodic half cell, for example. Or let's say if you know that this electrode is zinc, then you can say that this solution is zinc half cell solution, for example. So you will say zinc half cell solution. It's going to be 2 plus. But you cannot at all call this solution anode, just anode. Anode is an electrode. It has to be a solid metal, just to make that clear. Okay, so one of the mistakes that the students do in the exam, when we ask them what is this over here, they will say anode. No, this is the anode. Anode is an electrode. You wanna refer to the solution, you can say anodic solution, or the solution in which the anode is immersed, or the anode half cell solution, but do not just say anode. Now, let's move at the cathode. Let's say the cathode over here is copper, for example. So this one is gonna be the cathodic solution, or what you call cathode compartment, or you can say copper half cell solution. So you can use any of those words. Now, what else I have on this figure? This is the salt bridge. So over here is the salt bridge. Now, in the salt bridge, I have a flow of ions. Now, how this flow goes. So suppose you have a salt bridge. Let me just give you some examples of salt bridges. Examples of salts that comes in the salt bridge. NaCl. So we're talking about Na plus Cl minus. KNO3. We're talking about K plus NO3 minus. Or for example, KCl. So I'm not going to write it. You have a lot of ions that are used. LiBr. So all of these could be salt bridges, ions used for the salt bridge. Now let me take the first one. Let's say Na plus and Cl minus. So what happens here is that the positive ions, they go toward the solution that is consuming the positive ions. Yani it goes toward the cathode. So I have Na plus going towards this direction. So I think, let me see, cation, anion. Okay, so I think here I'm gonna write cation, they flow to this side. They flow to the cathode. Okay, and I have the Cl minus going toward this direction, or any anion. Here I also said any anion, it comes to this anions, it's come to this direction. If I want to talk about the flow of direction of the electric current, so the electric current goes opposite to the electrons. The electrons, they go this way. And I think that's it. What else can I write? Here, there's a gain of electrons. Here, there's a loss of electrons. I have here a reduction taking place. Here I have an oxidation taking place. This is the electrode that is gonna gain mass, and this is the electrode that's gonna lose mass. Okay, now about the reactivity, in this case, the zinc is gonna be more reactive. This is the metal rod of more reactive metal. So more reactive metal because it's the one that's going to get oxidized. And here the copper or whatever metal at the cathode we have, it's the metal rod of the less reactive metal that is gonna undergo a reduction. One more thing, the cathodic solution, it contains the oxidizing agent, contains the oxidizing agent, and this is the anodic compartment that contains the reducing agent. So all of these information, you need to know them, or you can watch a video on my channel in which I explain in details the parts of a galvanic cell. So expect any question in the exam about annotating or indicating something on a given cell diagram. Next, explain the cell notation below to answer the questions. Now I have added this one over here because the KPI also involves explain what cell notation means and write the cell notation for reaction occurring in electrochemical cells using an inert electrode. This cell notation doesn't use an inert electrode, but this one over here uses an inert electrode. And when do we use an inert electrode? When the anode, for example, involves a solution and another solution, like there's an oxidation occurring between two solutions, or oxidation occurring between a gas and a solution, like in this case over here. So there is no solid material to which we have to hang the alligator clip, the wire, so that the electrons can be transferred toward the cathode. So we need an electrode, a metallic electrode, and it has to be inert because it should not participate in the reaction. We don't want to change the results of the reaction. It is just there to allow the anode. The anode is usually represented on the left side of the cell annotation. It's simply going to allow the electrons coming out from the anode to go toward the cathode. So they need a medium. So we put an inert electrode. Now, if I move on the other side after what we call the salt bridge, we have the cathode. So this is the anode compartment and this is the cathode. So cathode half cell. Here I'm going also to say cathode half cell. So since this reduction is occurring between Fe to Fe 3 plus, I think it has to be the opposite. So that's reduction. Well, here it's written in the opposite way. So this is the cathode. So because I have a solution, two solutions, so I need a metallic electrode to drive, to allow the passage of electron. So we're going to use an inert electrode. Okay, so let's now annotate this one that is given in the question. So always there's two lines, vertical line, so that's the salt bridge in the middle. What comes to the left of this line is the anode compartment. Anode compartment or anode half cell. That's the anode electrode, and that is the anodic solution. And the reaction occurring at the anode is zinc going to Zn2 plus 2 electrons. So I'm explaining this cell notation. So that is a reactant, and that is a product. Product, reactant. Now, on the other side, I have the cathodic compartment, the cathode compartment, and this is the cathode electrode, and this one here is the cathodic solution, and that's just the phase boundary between them. Okay, now at the cathode I have copper solution going to copper. I have a reduction of copper solution into copper solid. So here's the reactant, and here is the product. Now, also, sometimes they give you a cell notation and they ask you to identify the reactant and product. We already did. To identify the oxidizing agent and the reducing agent. So Zn undergoes an oxidation. So this is the reducing agent. So the one here is usually the reducing agent, and the one here is the oxidizing agent. This is the one that loses mass. That's the electrode that loses mass, and that's the electrode that is gonna gain mass. Now, when they ask you for the overall equation, you're gonna take zinc plus the first two added to each other to give the products solid. So basically that's everything. Maybe they might make the question harder and ask you what happens in the salt bridge. So in the salt bridge, the negative ions goes on this side and the positive ions goes on this side. Okay, now consider the following galvanic cell that operates spontaneously. Okay, so they told me that this is a galvanic cell. So they told me that E cell is positive, and they told me that delta G is negative. And the information below to answer the questions. So when I have a reaction like this and they told me that this is spontaneous, since there are no indication on the cell over here, in order for the E cell to get it positive, the one with the higher voltage, see, I'm comparing those two voltages. The one with the higher voltage is gonna be the cathode, and the one with the lower voltage is gonna be the anode. That's how it works. Okay, now usually when they ask you to write the reaction at the cathode and the reaction at the anode, you just take them from here. One, you keep it as it is, and the anode, you just flip it. So let's break this question and pretend that they ask us to write the equation at the anode, and then they asked us to write the equation at the cathode, And then they asked us to write the balanced redox. So at the anode, it's going to be the opposite. So Cr gives Cr2 plus and 2 electrons. Don't forget the physical states. And at the cathode, you just copy it as it is. Now, you look at the electrons are equal, loss and gain is equal, so I'll just copy them as they are, and here's the final equation, redox reaction. On the diagram above, so let me just annotate, zinc is the cathode, this is the cathode, and this is the anode. So this is the cathodic solution or cathode compartment, and this is the anodic solution or anode compartment. Now on the diagram, indicate in which the direction flow they go from the anode towards the cathode, or I can simply do like that for the electrons. Okay. They might ask you to calculate E cell. Let me just add this question. So it is E cathode minus E anode. So it's going to be negative this one minus 0.91, and the answer is always in volt. Now moving on to the standard hydrogen electrode. Now the standard hydrogen electrode is a simple one. You just have to know how to describe it. So I have a half cell. See here, describe the standard hydrogen electrode. I have a half cell in which there's a platinum wire, there's a platinum electrode, because this one involves the transfer of electron between a solution and gas. So we need a platinum electrode, and this platinum electrode is immersed in an acidic solution. And when I say acidic solution, it means that this solution contains H plus ions specifically at a concentration of 1 molar. Now, also, there's a tube that allows the passage of gas. So hydrogen gas can come in or come out depending on whether this half cell is doing oxidation or whether it's doing a reduction. So the hydrogen gas over here, it should operate at a pressure of 1 atmosphere. Now, one important thing is that the standard reduction potential of this cell is 0 volt. Okay? Now, this cell, I describe it as the joker electrode because it can do both. It can undergoes reduction, okay, and it goes in this direction, gas plus 2 electrons, and it can work as a cathode if it's placed with an anode, and whatever voltage we obtain, that would be the voltage of the other half cell, because this one, the volt is always 0. And it can undergo an oxidation, and in this case, it's like that. Also, the voltage will be 0. So that's the only one with a voltage 0. It helps us determine the voltages or the reduction potentials of all the other cells. Write the cell notation of a galvanic cell where the standard hydrogen electrode is the anode. So I'm gonna do this one, and the other one is the cathode. So as you know, there's the salt bridge. On this side we put the anode, on the other side we put the cathode. Now if the hydrogen cell is operating as an anode, so it is hydrogen gas to hydrogen ion. Now, one important thing, I need to involve the inert electrode. So I write it at the beginning. So platinum, and you can do slash or you can do a comma. It doesn't matter. Okay? So just like the one over here. Okay? Here they put slash or I can put comma. Also, there's one important thing when you are writing the cell notation, and specifically because we have them, hydrogen gas, I need to say that it is at 1 atmosphere, and it's gonna change into positive hydrogen ion at 1 molar. You need to put the concentrations. Now, in the other cathode, it's going to be a reduction from Cu2 plus to Cu. So you're going to say Cu2 plus aqueous. Now, logically, the concentration must be given solid, like that. I don't need an inert electrode because there is already an electrode. Consider the cell notation below to answer the questions. The double vertical line represents the salt bridge. And write the equation at the anode. It's zinc 2 Zn2 plus 2 electrons. Calculate the electrochemical cell standard potential of a voltaic cell with overall reaction below and its redox reaction or and identify whether it's spontaneous or not. So let me just look at this equation over here. When an equation is given to you, how do you know which one is the which one is the anode and which one is the cathode? And the E cell reduction potentials are given over here. Now we look at only one of them, the easiest one for us. So lead goes from 0 oxidation state to 2 plus. So this is the one that did oxidation. Therefore, this is the one operating at the anode, and this is the one operating at the cathode. You're done. Now, E cell is equal to E cathode minus E anode. So it is 1.07 minus negative 0.13 volt, and the answer is 1.2 volt. Now, since E cell is positive, so the reaction is spontaneous. So which sign of cell indicates that a reaction is thermodynamically favored? A positive one. Which sign of E cell indicates a thermodynamically unfavored? It's going to be negative E cell. Explain how E cell is calculated. You need to remember this formula because it is not given to you in the formula unit. So, which sign of E cell indicates a thermodynamically favored? Positive. So that is, for this one, non-spontaneous. 0, we have it when we are dealing with a concentration cell, and the concentrations of the two half cells are equal to each other. So at that point, the voltage will be 0. Explain why a positive E cell indicates a thermodynamically favored reaction. Because when E cell is positive, it means that the delta G is negative, indicating that I have a thermodynamically favored reaction. Now I'm going to show you something here in the formula sheet. You see this one? So delta G is equal to minus NF E cell. If this was positive, Faraday is a constant and N is the number of moles involved in the transfer, electrons transferred. So a positive multiplied by negative value, we get delta G to be negative. Now, if this is negative, and there's another minus over here, then the answer of delta G is going to be positive, and it's going to be a non-spontaneous one. So remember this formula. Use the standard half cell potentials listed below to calculate the standard potential for the following reaction occurring in an electrochemical cell. Again, I have the standard reduction potentials. I need to look at the equation and know which one is anode and which one is cathode. If this is hard for you, look at the easy one. From 0 to plus 3, that is an oxidation. Here, this is 0 to minus 1, that is a reduction. Anyway, 1 is enough. So that is the anode, and that is the cathode. Oxidation occurs at the anode. So E cell over here is cathode minus anode. And the answer is 1.40 volt. It's positive, so it is spontaneous. On to section subtopic 4.3. Write the equation used to calculate the E cell from delta G standard and identify what N and F stands for. So you have this formula in your formula sheet. Delta G standard is minus NF E cell. Now, delta G stands for the Gibbs free energy. N is the number of moles of electrons transferred. N is usually in mole electron per mole. So it's the amount of electrons transferred. And F is the Faraday constant. And it is given in your formula sheet. It's equal to 96485 C Coulomb per mole electrons. It's given in your formula sheet. And E cell is the one in volt. Now, I want to show you here in your formula sheet that the voltage is Coulomb, joule per Coulomb. Here is Faraday constant. It's over here. Don't forget this. Now, the delta G, if you have a question to solve and calculate delta G from a value of E cell, you must not forget to divide this by 1000 because the volt is joule. It's in joule. This one. So I need to divide it by 1000 to obtain my answer in kilojoule. Now the unit goes as follow. I'm just gonna explain it, the unit, and justify again what we divide over here. So let me just show you this one. Kilojoule, delta G is gonna be kilojoule per mole. Now this N, I'm gonna write it again, is in mole electron per mole. Faraday constant is Coulomb per mole electron. And the voltage, you have it in your formula unit, it is joule per Coulomb. Now when you divide over 1000, you are converting this kilojoule to this joule to kilojoule. So if I divide this by 1000, I'm gonna get it in kilojoule. So the Coulomb cancels out, the mole electron cancels out, and the final unit is kilojoule per mole, which is delta G. Now, let's continue. So write the equation used to calculate E cell from K. Now again, E cell is RT over NF ln K. Again, I'm gonna show you this in the formula sheet. It's over here. You don't have to memorize it. You see this one? I have these two formulas over here. So if I say minus RT ln K equals minus NF E cell, so minus and minus, they cancel out. So E cell is RT ln K over NF. Here's the formula. Let's continue. Calculate E cell if K is 1 times 10 to the power 4. Note that this K over here is above 1. So we are dealing with a spontaneous reaction and we expect the value of E cell to be positive. Now, the reaction is given over here. I have zinc to zinc 2 plus. There are 2 electrons lost. And silver to silver, 1 electron is gained, but we need to multiply it by 2. So the N here is equal to 2 moles of electron per mole. And calculate E. So I'm going to use this formula written over here. So it's equal to RT over NF ln K, and I am going to substitute. R is 8.314. I'll give you the units. Now the temperature, if temperature is not given, we're gonna take it as 298, and if it's given, then that's good. 298 Kelvin, and the electrons over here is 2 mole of electrons per mole, and Faraday constant is 96485 coulomb per mole electron. So mole electron and mole electron, they cancels out. And K, this one is in Kelvin. Now for the R, I'm going to show you the unit of R over here. R is over here. It is joule mole minus 1 Kelvin minus 1. So it's joule per mole Kelvin. Joule per mole Kelvin, and the temperature 298 Kelvin. So Kelvin and Kelvin, they cancels out. Mole and mole, they cancels out. And I'll get the answer as joule per coulomb. And that is true because the volt is in 1 coulomb per, a joule per coulomb. So here's the unit of the voltage, E. And I'm gonna put here ln K. K doesn't have a unit. So if we plug this into our calculator, 8.314 times 298 over 2, and Faraday's constant, ln, I'll get an answer of 1184 volt. Note that in this formula, you don't have to do any conversion because the volt is in joule per coulomb and not kilojoule. What is the voltage of a concentration cell when the ion concentrations in both cells are equal? So when the ions in a concentration cell are equal, I'm just gonna draw a concentration cell. Here's the electrode. So suppose we have copper. So the solution, they both have to be the same. So that's the important thing in the concentration cell. That's the salt bridge, and these electrodes are connected. A concentration cell is a cell where the anode and the cathode uses the same solution and they have the same electrodes. Now usually if the concentration here and here are different, there is a voltage. But when the concentrations are equal, so let's say this is 0.5 molar and this is 0.5 molar, at that point the voltage, so when the concentrations are equal, the voltage is equal to 0. Explain why no current flows in a concentration cell when the concentrations are equal. Because to have a current, the concentrations must be equal, and the higher concentration will decrease, the lower concentration will increase until both they become equal. And at that point we say that the concentration cell is discharging and eventually the voltage will become 0. So without any difference in concentration, without any differences in the concentrations of anodic and cathodic compartment, there won't be a driving force for electron flow. There won't be a driving force for the electron flow, and that's why the E is 0. Now next, which type of reactions are driven by electrolysis? It's a non-spontaneous redox reactions. In the electrolytic cell, again, this is negative. Why an external source is needed? Because in electrolytic cell it converts electrical energy into chemical energy, so it requires an input of since it is non-spontaneous, so since it is a non-spontaneous mechanism, a power source or an external energy source is needed to drive the non-spontaneous redox reaction. Now, before we move on to questions here, what are the products at the cathode and at the anode during electrolysis of molten? I would like to point at when I have electrolysis of molten, it means that the ions are in their liquid state, because electrolysis of molten metal or of molten ionic compound, it operates at a very high temperature, and at that point there is no water over here, so the medium is liquid, the liquid state of these ions. Okay, so usually there's a different kind of question. They might ask you what is deposited at the anode and what is deposited at the cathode. So a same like this question here, what are the products at the cathode and anode? Or they could say, what is deposited at anode or what is deposited at cathode. That's the same meaning. It means they are asking you what do we get at the anode and what do we get at the cathode. Okay, so you need to understand that the anode is the positive electrode in electrolysis and the cathode is the negative electrode of the electrolysis. Therefore, the positive ions, they are gathered around the cathode and they turn into metal, and the anions are attracted to the anode and they turn into like for example here Br2. Now, because these are liquids, what I obtain and the temperature is really high over here, the potassium obtained is not a solid. The potassium obtained is liquid, and Br2 in this case is a gas. It's obtained in the gaseous state because the temperature is really high. It's above the melting point of any metal. Now the rule goes as follow. If the salt given in the molten electrolysis, so I'm just gonna put XY. If XY belongs to group 1, like if the metal here was sodium, potassium, or lithium, they are always obtained in the liquid state. If the metal is belonging to group 2, an alkaline earth metal like magnesium and calcium, also in the liquid state. But if we are dealing with, let's say, transition metals, usually the transition metals, their melting point is very high. It's above the temperature used in the electrolysis. So like copper, iron, nickel, they are obtained at the solid state. So here, what are the products at the cathode and anode during the electrolysis of molten KBr? You will say at the anode we will obtain bromine gas, and at the cathode we will obtain liquid potassium. Again, use the diagram below to answer the questions. Be careful when you are looking at electrolysis. Look first whether it's an electrolysis of molten or aqueous solution. Because if I have aqueous solution, it involves the ions coming from water. So we might obtain hydrogen gas at the cathode and oxygen gas at the anode if it was in aqueous solution. Now, I have here molten, so let me see the questions, write the overall. Okay, so let's split this. This is the cathode, this is the negative electrode, and this is the positive electrode. In molten KCl, I have liquid potassium and liquid chloride ion. So the chloride ion is going to gather around the cathode and the potassium is going to gather around the anode. Now at the anode, I have oxidation. I have Cl minus going into Cl2 gas. I need to balance it. So as an answer, that's the half equation at the anode. At the cathode, I have potassium reducing into potassium metal in the liquid state. Don't forget the physical states here. Now, since there's a loss of 2 and a gain of 1, this must be multiplied by 2, and the overall equation is 2K plus and 2Cl minus, giving me Cl2 gas and 2 potassium liquid, or this one could be written like that, 2 KCl liquid going into Cl2 gas and 2K liquid. Okay, So here. Now, explain the electrolysis of sodium iodide using inert electrode. Oh, be careful. Sodium iodide aqueous. Using inert electrodes given the electrode potentials. Now, let me just explain this here. When I have aqueous, it means at the anode, and here the cathode. At the anode, which is the positive electrode, I have the I minus approaching the anode, and you know H2O, it has two ions, OH minus and H plus, and I have OH minus coming over here. And at the cathode, because this is negative electrode, I have the potassium aqueous and the hydrogen ions from water. In this case, we need to look at the possible oxidations happening at the anode and at the possible reductions happening at the cathode. I know that I explained in class that whenever I have group 1, so it's hydrogen gas obtained, discharged at the cathode, and whenever I have Cl minus or Br minus or I minus, I will obtain I2 or Cl2 or Br2 at the anode. But this question, they want the answer in a different way. So we look at the electrode potentials. Now note here that both of them are represented as oxidation. So fine, we're gonna compare them as they are. So which one is the higher one? This one. So this is the winning oxidation at the anode. So like I said, I minus is gonna undergo an oxidation, and I'll compare the reduction that might happen at the cathode. So this is -2, it's so low. This is -0.41, it has the higher voltage. So this is the winning one. So like I said, these two are the one that's going to be discharged. So in this case, 2 electrons lost, 2 electrons gained. You're just gonna add them up and write the overall equation, which is the one over here. So explain, I mentioned this explanation already. So now I'm just gonna write it. At the anode, I minus will be oxidized to I2 and not OH minus to oxygen gas, because the reduction potential of I minus to I2. Okay, wait, let me put oxidation potential, because here they gave it to me as an oxidation potential. So the oxidation potential of I minus to I2 is higher than the oxidation of water to oxygen gas. And at the cathode, cathode, sodium ions are not reduced, or I can say water is reduced to hydrogen gas. So either ways, because their reduction potential is lower than the reduction potential of water into hydrogen gas. So I hope that this is clear. Now, identify 3 uses of electrolysis in industry. Which of the following is not an industrial application of electrolysis? Electroplating is a use of electrolysis, so this is correct. Production of chlorine gas, yes. Purification of metals, so I can purify a metal. For example, aluminum oxide undergoes electrolysis in order to obtain aluminum, but it's not used for combustion. I'm going to give you the application, all the application of electrolysis, just in case the multiple choice changed in the exam. So electrolysis is used for metal extraction. Okay, so that is 1. 2, electrolysis, metal extraction, and specifically for reactive metals that they cannot exist alone in nature. It is used to make gases like chlorine gas, hydrogen gas. So we say brine electrolysis. For example, brine electrolysis of aqueous sodium chloride. Other uses or industrial application for electroplating, like we electroplate with gold. We plate a metal with gold or with nickel, so it's like protective coating, protecting something from corrosion. Protective coating, protecting a metal from corroding. And for electro-refining, like for example refining copper, is just to purify metals. And finally, an important use of electrolysis is the electrolysis of water. Usually this is done in the hydrogen fuel batteries. Okay, so just in case, to be on the safe side, if they changed the multiple choice given, the choice is given, and they ask you to select an industrial application of electrolysis. Okay, so here it comes. List the 3 industrial uses of electrolysis. So I just gave you 5. So let's say metal extraction, or first electroplating, metal purification or metal extraction, for example, and hydrogen fuel cell, or you can simply say electrolysis of water. So you can choose any of those. Moving on, the mass of aluminium produced in 1 hour by the electrolysis of molten aluminium chloride, if the electrical current is 10 ampere, is how much? Now, to use these questions, you have 2 ways. You either memorize the formula that I gave you in class, or you can use the units. The formula that I'm asking you to memorize is mass is equal to the current multiplied by the time must be in second, divided by Faraday's constant, multiplied by the molar mass in gram per mole, over the amount of electrons transferred, moles of electrons transferred. Now, if I use this formula, so they want the mass of aluminium produced in 1 hour. So 1 hour is gonna be multiplied by 3,600 in order to turn it into seconds. So I'm gonna put it over here. 1 hour times 3600 by the electrolysis of molten AlCl3 if the electric current is 10 ampere, so that's I ampere. Now Faraday's constant is 96485, and N, since here I have aluminium involved, so you really need to show the equation with your answer. So aluminium AQs plus 3 electrons gives aluminium. So here I have N equal to 3 moles electrons per 1 mole of aluminium. So plugging this into your calculator, the answer is going to be 3.36 gram. Now, what do we do just in case we couldn't remember this formula or we have a mistake in the formula? So let me just give you a very simple technique. You're gonna need from the formula sheet the fact that 1 ampere is coulomb per second. Faraday is 96485 coulomb per mole electron, and you're gonna need the fact that molar mass is in gram per mole. So let's see how we're gonna use this. And yeah, in this equation, N, the amount of mole, is 3 moles of electrons per mole of aluminium. So let's put the pieces together. If I want the answer, they are asking me to calculate mass. So I'm gonna say mass in grams. And I'm gonna start with the unit over here that has mass in the denominator. So in this one, oh, I think here I forgot to add the molar mass of aluminium in here. The mass of aluminium, you don't take the molar mass of aluminium chloride. It's just the mass of aluminium. You can get it from the periodic table. Apologies for this mistake. Anyway, when you try to calculate this without the 27, you're gonna see that you're not gonna get this value. So here we must not forget the molar mass. Anyway, let's continue the unit way. So I need mass. The molar mass is the one containing gram per mole, and I want gram to be in my answer. So I'm gonna start with 27 gram per mole. Now I'm done with this. I'm gonna continue. I have mole introduced in here. So I'm gonna use the mole N, but in here I want to cancel this mole by this mole. So I'm gonna flip it. So I'm gonna say 1/3 so that I can flip those units. So it's gonna be mole over mole electron. Okay, I'm done with this. Next, I'm gonna use the current, and the current here is given as 10. So I'm gonna put 10 coulomb per second. I'm done with this. Now I still need to use Faraday over here. So if I want to use Faraday, I want to get rid of the current of the coulomb. So I'm gonna flip those. So I'm gonna say 1/96485 mole E over C. When you are using this way, just keep the units very clear so that you don't get confused in the simplification. Now I'm done with all of those over here. I still need to get rid of the time. And in this one, they gave me 1 hour. So I'm gonna put 1 times 3600 seconds and now seconds and seconds are cancelled out. So 27, here it is. These are here. And Faraday and 3 are here. So you are going to get the same answer. Moving on to the last part included in our exam, it's those KPIs. Now I know the questions to those KPIs are limited, but I'm just gonna go through every KPI one by one and I will explain it. So here, identify the type of batteries that are common in cars and specify how they can produce 12 volt when a cell only produces 2 volt. What does that mean? So KPI 4.3.21. Anyway, I'm also gonna talk about the reason a lead acid storage battery goes dead. So both of them 21 and 22. So first of all, the lead acid storage battery. This is the battery that is used in cars. You know, a car needs a battery inside, so all of the battery in the cars are, it's most commonly used. Now, this lead battery is made up of 6 cells inside it, and each cell produces or has a voltage of 2 volt. So 6 times 2, this is how a car battery it operates and generates, or it's a 12 volt battery made up of 6 connecting cells in series, like one after the other. Okay, so it's like the positive end of one cell is connected to the negative of the next, and so on. So that's why I said cells in series, and the voltage adds up until we get 12 volt. Now, the reason why lead acid storage goes dead. So let's give you the first reason. It's called sulfation. So in this cell, we have the solution of lead sulfate, Pb, SO4, in it. So crystals of lead sulfate will start building up, on the plates. So what does that do? It reduces the surface area. As a result, it reduces the surface area of those plates, the cell plates that are operating, and less chemical reactions will happen. So it's not comfortable in working, so it starts like dying. Or another reason why the lead acid battery goes dead, it could be electrolyte depletion. And we mean by this, in the car, there's a high temperature in the radiator and so on. So the temperature near the engine is very high. So with time, the water inside the battery evaporates. So I don't have any solution medium anymore. So we call it electrolyte depletion. And the third reason why a lead battery goes dead, it's because of the internal short circuit. So could be a damaged separator or corrosion causes shorting of the battery. Okay, So when the battery can no longer produce sufficient current for the car, it goes dead. So the first question, what is the primary reason for lead acid battery to cause dead? So the primary reason is the sulfation of the plates. Okay, this one is not a main reason. It can happen. Okay, so it's the primary one is the sulfation. Now, the next KPI specify 3 types of rechargeable batteries other than the lead acid storage battery. Of course, the battery of the car is a rechargeable battery. You don't change it like frequently until it dies. So 3.23 KPI. Also here I have the nickel cadmium battery. It's NICD. This is a rechargeable battery. You can recharge it. Or the nickel metal hydride, which is symbol NIM hydride, and a lithium. These are the most common one. Lithium ion. Okay, so you know the lithium ions are the one used in smartphones, laptops, tablets. So you just plug it into the charger and you charge it. So these are rechargeable batteries. So which of the following is not a rechargeable battery? That's a rechargeable battery, so that's not the answer. Nickel metal hydride and nickel cadmium are rechargeable batteries. So the alkaline are non-rechargeable. You know, the alkaline, these are the batteries that you use in the toys and you throw it after a while and you change it. Okay, and explain why cadmium-based batteries such as nickel cadmium are being replaced. These are not really used anymore. So here comes the question, the issues associated with cadmium batteries. You know cadmium, so first of all, it's the toxicity coming from cadmium metal. Cadmium metal is very toxic and it's considered as an environmental hazard. So that's why we replace them. Another example, it poses disposal and pollution risks. So we have other safer alternatives like nickel metal hydride or the lithium ion batteries are being used nowadays. So there are other problems caused memory effect. So the capacity reduces if repeatedly recharged before fully discharged. You know the cadmium batteries, when they are when the battery is fully discharged, you need to recharge it again. However, if you recharge it before it's fully discharged, one time after the other one time after the other, so it reduces its capacity. So the capacity is reduced if repeatedly recharged before fully discharged. And as I said, better alternatives and safe for the environment are the nickel metal hydride and lithium ion batteries. They have better energy, higher energy, and safer. Now I have here Another KPI, identify the most common uses of lithium ion batteries. So most common uses of lithium batteries for smartphones, laptops, tablets, iPads. So these are also, we can use them in electric vehicles like drones, power tools. Okay, now why they are used? As I said, they have higher high energy density, and they're light, they're not so heavy, and they live longer. Okay, now for the last one, explain how a hydrogen fuel cell works and indicate the anode, the cathode, and direction of electron flow. So, um, basically, the basic reaction or hydrogen cell, it's the electrolysis of water. So the hydrogen gas enters the anode, and the hydrogen molecules, they split into protons and electrons at the catalyst. So the electron flow through an external circuit which produces an electric current. The protons pass through the electrolyte to the cathode, and oxygen at the cathode reacts with protons and electrons to form water. So I'm just gonna write it here. The anode, which is the here in the fuel cell, is the negative electrode, and I have the hydrogen gas changing into H plus, producing, as I said, protons, and electrons are released. And at the cathode, I have the oxygen gas from the atmosphere, because you know a fuel cell can use oxygen. So here's the oxidation reduction reaction. So it forms water. So the electron in the fuel cell, they flow from anode to the external circuit to the cathode, and that's how the electric current is produced. So the importance of hydrogen fuel cell is that this is a battery that gives me energy to like a car operates on hydrogen fuel cell. It's a clean energy. Only water is produced, and water is safe. And the electron, they flow outside the cell of the hydrogen fuel cell. This is how electrical work is done. You know, this is how the battery produces electricity. And the protons, they flow inside throughout the electrolyte, the solution, through the electrolyte solutions, which completes the circuit. And that's it. I've added some additional practice questions, and you can look at the end. Here I have some more questions related to the batteries. So you can solve these questions. I think they are somewhere here. Here. Okay, so in the last part. So all the best in your exams, and good luck.